start. So section 3.6 rational function. So just as a quick review, I want you to remember that a rational function, so a rational function is of the form p of x over q of x. So we call that r of x pretty much for the fact that r just stands for rational function. And then p of x is a polynomial, so p of x is a polynomial, and then q of x is also a polynomial. And the other thing, of course, is that q of x is not equal to 0, or the denominator cannot equal to 0. So therefore, the domain of R of x is the set of all real numbers except those for which the q of x is equal to 0. So that's the basis for what we're going to talk about on the next page of page 245 on the definition of the vertical and the horizontal asymptote. So let me move along to that here. I'll just throw those on the floor, that's fine. So, all right, so the definition of the vertical and horizontal asymptotes. So the line x equals a is a vertical asymptote of the function y equals f of x. Here, let me focus that. If you can't see something at some time, let me know. But I don't actually think, I think that the focus went away a little bit because the light in the basement went off again, but that's okay. All right, so the line x equals a is a vertical asymptote of the function y equals f of x if y approaches plus or minus infinity as x approaches a from the right or the left. So this is actually y, this notation here is y approaches infinity as x approaches a from the right. So that little positive sign there next to the a, the superscript there means from the right. So this means that it's values that are bigger than a, and that a with the negative as the superscript means values less than a or to the left of a, and then this is y approaches negative infinity as x approaches a from the right, so that means it's going, the function, the y values are going to be going down as we get closer and closer to values of a that are a little bit bigger than a. And then we have something similar for this graph here for y approaches negative infinity as x approaches a from the left. And so the line y equals b is a horizontal asymptote of the function y equals f of x if y approaches b as x approaches plus or minus infinity. So you can see that that means y approaches b as x approaches infinity. So here we have that. But then y approaches b as x approaches negative infinity. We see that this is over here. So what you actually can see is that for a value like of y equal b value to be a horizontal asymptote, it doesn't actually need to, all right, it doesn't actually need to approach the b, like the value of b as we go to infinity and negative infinity, as long as it approaches b at some point, either on the right side of the graph as it approaches infinity, or the left side as it approaches negative infinity, then it is a horizontal asymptote. All right. So the other thing that you should notice is that if you look here, you see that the graph of the function actually did cross its horizontal asymptote. So that is possible, but a graph can never pass its vertical asymptote. So you see that none of these actually, if you look at them, passed over or crossed or intersected the vertical asymptote, but a graph can intersect a horizontal asymptote. All right, so hopefully that all makes sense that a graph can never intersect a vertical asymptote, but it could intersect a horizontal asymptote. It doesn't have to because this graph shows that, but it could. So a graph can never intersect a vertical asymptote. All right, so that is really one thing that you should keep in mind. So if I look at this example here, f of x equals 1 over x to the fourth, examine the numerical behavior of f of x equals 1 over x to the fourth as x approaches 0, and this negative sign means x approaches 0 from the left, meaning values that are a little bit less than 0. So a value that's less than 0 but close to 0, well, so that actually could be, let me see. That actually could be some value like let's say let's try x, and then we have f of x equals 1 over x to the fourth. Let's try like negative 0.01. All right, so if I do that, then I get 1 over negative 0.01 to the fourth power, and that ends up being, well, that ends up being 100 million. All right, and then if I try negative 0.00, let's just put in three zeros. So 1 over negative 0.0001 to the fourth. Well, that is, well, that's actually a pretty large number already. I don't even want to say what this is, but I think that you get the point that as we get really, really close to 0, that the numbers are getting very, very large. So then I would actually say that the numerical behavior is that y approaches infinity as x approaches 0 from the right. All right, so keep that in mind that I feel like we've talked a little bit about this type of stuff, but I wanted to make sure that you're completely clear on the notation because we've been talking about polynomials for so long and not as much about like more of these rational function behaviors. All right, so examine the numerical behavior of f of x equals 1 over x to the fourth as x approaches, so this is x approaches 0 from the right because of the positive superscript on the 0. So this means values that are a little bit bigger than 0 but still close to 0. So that might be x, and then f of x equals 1 over x to the fourth. But if I pick 0.01, I have 1 over 0.01 to the fourth. Well, I should get the same answer as up here. All right, so that would be 100 million again, and then the same thing for 0.0001. You should get the same answer as before. So hopefully this all makes sense that then in this case I would say something very similar. Y approaches infinity, whatever some really large number is, but again, we never know what infinity really is, as x approaches 0 from the, oh, I put the symbol. Yes, I think I put the symbol there. Yeah. So x approaches 0 from the right. All right. So now let's see. Where is, I really don't have the next page, but oh, yeah. Okay. So now I think that what you really want to pay attention to is a couple of things, and one of these things, and I'll bring it back down for a second, because one of the things is that if you're looking at whether there's a vertical or horizontal asymptote, all of the vertical asymptotes are x approaches some number a from the left or the right, but all of the horizontal asymptotes are are x approaches infinity or x approaches negative infinity. All right, so that's one thing that I do want you to remember, is that you want to make sure that you know whether what you're finding here relates to a vertical asymptote or a horizontal asymptote. So if I look at, in particular, like x approaches 0 from the left or 0 from the right, like I don't think necessarily um, get exactly why you would pick 0 just from the statement of the problem, but the issue is that, like this a value, all right, this a value that you have here is generally the value, well, generally meaning like that's all the time, is what we're going to be checking here, just the a values where the denominator is 0, because those are the spots where there's a possible asymptote. So if I look at this one, I know that x to the fourth cannot equal 0, so x cannot equal 0. So I want to check all of these as x approaches the a from the left, or x approaches a from the right, but I want the a to be the value where the denominator is 0, because that's where there's going to be the vertical asymptote. All right, so this 0 right here didn't actually come out of nowhere, just so that you know. So it's not always 0. It's whatever values are the values that would make the denominator equal to 0. So there are functions then that could have more than one vertical asymptote, because of the fact that there could be more than one value that makes the denominator equal to 0. All right, so keep that in mind also. So hopefully that all makes sense, that if we get y approaches infinity or negative infinity as x approaches a from the right or left, that means that this value of x equals 0 is a vertical asymptote. So you see that y approaches infinity or negative infinity, as long as we get that answer here, then that means that this x equals 0 is a vertical asymptote of f of x. So if you're wondering, like, why are we doing this, or what does this here mean, this means, all right, so this actually means something. It means that x equals 0 is a vertical asymptote. And this here actually means something. It means that x equals 0 is a vertical asymptote. So I do want you to keep that in mind, that there are actual reasons why we would want to do all of this. All right, so I pressed the wrong button, but that's okay. I think that you all have the general idea of this. And so let me go here. So describe the limit behavior as x approaches negative infinity. So let's just think of what might happen here. We remember f of x was 1 over x to the fourth, right? So if we have x and 1 over x to the fourth, and we want the behavior as x approaches negative infinity, right? So we can put in some, like, substitute some numbers that are negative, but really, really large negative values, just to see what this is. And if I pick like 1 over 99 to the fourth power, I get something very, very small already, right? So negative 99, so 1 over negative 99 to the fourth power, that's 0.0000000104 102 03 5 6. So then I'm pretty confident that I know that this is going to be almost 0. But if I want to try maybe a different number, negative 99999, I could, right? So negative 99999 to the fourth. So if I do that, I would get, well, 0.0000000000000001000004. All right, so, well, uh, I I hope that at this point you can see that, yeah, this is very close to 0, very small, very close to 0. So I feel like I can confidently say that y approaches 0 as x approaches infinity. So then again, this means something, right? So if I look back at my definition, if y approaches b as x approaches infinity or negative infinity. So the other thing that I think might help you here is to find the vertical asymptote. Y needs to be approaching infinity or negative infinity. But if you want a horizontal asymptote, it's x that needs to be approaching infinity or negative infinity. All right, so that's another thing to keep in mind, that is the difference between these as well. So keep that all in mind, and then try to bring this together. This then has a meaning, and this means that whatever this number is here, right? In this case, it happened to be 0, but whatever that number happens to be is the horizontal asymptote. So this means that y equals 0 is a horizontal asymptote of f of x. All right. So now we could do the same thing. I actually don't know why this one of these should have been positive infinity. That might be why I put actually the positive 99 first. So just make that positive infinity. So x, and then 1 over x to the fourth, and then we have 99. We have 1 over 99 to the fourth. Well, that should still give us 0.0000000104102035 And if I have 99,999, 1 over 99,999, I get .000000000000000000004. All right, I hope that you enjoyed that. Actually, if you noticed anything about this at all, I did actually group the zeros 5 at a time so that it would be easier for you to write out if you were following along at all. So because normally, like if I were writing this out, I wouldn't actually be able to recreate that as easily without going and counting every single zero. So if it helps you, like you don't have to write this one down unless you want a really good time. But if I do 999,999,999, then that one ends up being, like, just for fun, I happen to have this one written out already. It's .0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 .000000001. All right, and then some more zeros after that, but and then probably the 4 1 0 2 0 3 5 6 at some point. But I think that you get the point that this is a very small number. So once again, we had y approaches 0 as x approaches, that would be, that last one was negative infinity then, and then this one would be the positive infinity. So either direction here, as x approaches negative infinity or positive infinity, then I would say that y actually is approaching 0. So again, this is double checking that of course in this particular case it just gives us a double check that y equals 0 was still the horizontal asymptote. And so now, again, remember though, like it doesn't matter whether the y approaches b as x approaches infinity and negative infinity, because it only has to be from one side. But in this particular case, it approaches 0 from the case when x approaches negative infinity and from the case when x approaches infinity. So now, last item here is to use this information to sketch the graph of f. So what did we know? Well, we know that from part A, we had part A? Yes, we knew that y approaches infinity as x approaches 0 from the left, and then part B, y approaches infinity as x approaches 0 from the right. Part C, y approaches 0 as x approaches negative infinity. And part D, y approaches 0 as x approaches positive infinity. So then we can use all of that information to graph this function here. So let's graph this function here. And as x approaches 0 from the left, we knew that y was approaching infinity. So I am going to just draw something that goes up to infinity like that, and then as y approaches infinity, as x approaches 0 from the right, so that would be over here. And I see that as we get closer and closer to 0, this needs to go up to infinity. And then y approaches 0 as x approaches negative infinity. So here is x is negative infinity, but y needs to be approaching 0. So I know that it's going to come down here and look like this. All right, and then the same thing over here on the right, as x approaches positive infinity, y is approaching 0, so it needs to come down and look like this. So this is f of x equals 1 over x to the 4th. So really, the main thing that I was focusing on here is making sure that you know what the notation means, and that you can see by looking at the notation or from the graph whether there is a asymptote or not. So you can see hopefully that right here is the horizontal asymptote. So y equals 0 is a horizontal asymptote, and then we had x equals 0 was a vertical asymptote. So x equals 0 is a vertical asymptote. All right, so that is it on the basics of the notation in the asymptotic behavior is what we call it here. But now this particular one, of course, I could graph using transformations of or things like that, or looking at the parent function, or by plotting points. There are lots of ways that we talked about actually the graphing of functions, but I do think though that this is just giving you a little bit extra so that you know what the graph should look like, even if the like your calculator or something like that gives you something that looks a little bit strange. So again, if you have any questions, feel free to put them in the chat. But I'm going to talk about the next page here, and this is actually just in a way, a shortcut. All right. So if I look at this, I already told you that for rational functions, we really just need to figure out where the denominator is equal to 0 to find the vertical asymptotes. But there are ways to figure out the horizontal asymptotes without like substituting in large values for x and seeing what happens. All right. So if you look at the rational function and the numerator and the denominator are polynomials, all right. If the numerator is of degree n and the denominator is of degree m, so we look at the leading term for that, then if n is less than m, then the horizontal asymptote is y equals 0. All right, so just keep that in mind, that the n is the numerator and numerator's degree, and m is the denominator's degree. So I usually forget which one is which, so I just put degree of the numerator is less than degree of the denominator, just so that I don't forget which one is which. All right, so if you look at the example here, you see that the degree of the numerator was 1 because it's just the first power here. So this was degree of the numerator was 1, and the degree of the denominator was 2. So since 1 was less than 2, we see that there was a horizontal asymptote of y equals 0 here. But then you can also see that if you look here, that x could not equal 1 and x could not equal -3. So there are the two vertical asymptotes. All right, so x equals -3, x equals 1, and y equals 0 were the three asymptotes for that particular rational function. So these were not really, in my opinion, very difficult to find. You just had to know what to look for. All right, now, if the degrees are equal, then the horizontal asymptote is the ratio of the leading coefficients. So that would be, again, if the degree of the numerator equals the degree of the denominator, then the the horizontal asymptote is just the ratio of the leading coefficients. All right, so what do I have here? Well, for this example, I have that it's 3x plus 1 over x minus 2, so the degree of the numerator is 1, and the degree of the denominator was 1, so 1 equal 1, so that meant that 3x over 1x was the horizontal asymptote, so you get y is equal to 3. So you can see that right here, y equals 3, but then I also knew that this denominator could not equal 0, so x could not equal 2. So here is the vertical asymptote, so there's x equals 2 and y equals 3. Those are the two asymptotes for this function. All right, so now here's another one. Here is where you have the degree of the numerator is actually bigger than the degree of the denominator. All right, so the degree of the numerator would be bigger than the degree of the denominator. And so here we have degree of the numerator would be 3. Degree of the denominator would be 1. So 3 is greater than 1. So what does that mean? That only means no horizontal asymptote. All right, so now what you should also notice though is that the denominator x cannot equal 2. So this so there is a vertical asymptote at x equals 2. But then it said, if you see here, there could be a possible, and I will reiterate, a possible slant or oblique asymptote, but no horizontal asymptote. So how would you find that asymptote, that slant or oblique asymptote? Well, what you actually do is you do the long division. So it's x to the third minus 1 divided by x plus 2, and then you would just see then what is going on here. So then I will use, actually, just so you know, I will use the synthetic division here. So I'll take the c value, the see, this doesn't seem right. This actually does not seem right, because I see that that's 2, and this says, I didn't actually get that from the graph, so I think that's supposed to be minus 2, because I didn't even get that from the graph. Now that I see, I got the asymptote from the graph, not looking at this. So I actually think that that was a typo in the graph now that I see that. But let me double check here, because I know what I was going to show you next. But if it's some strange thing, then yeah. All right. So now, oof, yeah, So anyway, I don't know why that was should have been a minus down here, because that's what matched up with the graph. But this is right now with the minus being down here. But so what I'm actually going to do is I'm going to take the opposite of this, the C value. So I actually am going to get my whiteout here to make sure that I change that to minus. And this, oh no, this cheap whiteout again. Unbelievable. All right, so yeah, you can see this whiteout is very cheap. Boy. All right, so now I take the opposite of the negative here, so I need the 2, and then I have, again, 1x to the third, 0x squared, 0x minus 1, and then I bring down the 1. 2 times 1 is 2. I add these together, 0 plus 2, 2. 2 times 2 is 4. I add those together, 4. 2 times 4 is 8. I add those together, I get 7. So what this means is that this equals, all right, it equals x squared plus 2x plus 4 plus 7 over x minus 2. So whatever this part is, here the actual quotient, not the remainder, but the quotient is actually the asymptote. All right, so just keep that in mind, but I actually can factor that into x plus 2 all squared, so that is actually the asymptote here. But if I try to graph that just so that everyone is clear on what is going on here. So if I graph x plus 2 squared, oof, well, all right. I was trying to actually make sure that you could see this clearly, but I guess what I'll do is, because if I look at this, like you can't actually see this part of the graph over there. So let me set the window so that you can maybe see it a little bit better. So negative 20 to say 20, I'll scale by 2, and then negative 10 to 100, I'll scale by maybe 2, and then hopefully maybe you can see this a little bit better. So there was the graph of the function and then the graph of the asymptote, all right? So if you looked at how this occurred, all right, if I just look at, I'll do I want it to actually show you it being graphed out again so that you can tell which one is which. But anyway, it looked like this. All right, so all I really want you to notice is that you see that as we go out to x approaches negative infinity or infinity, that the ends of the function really get really close to this parabola. All right, that's what I mean by an asymptote that is oblique. It means one that is not a line. All right, like a horizontal line, because you could have a slant one, like in the next example, that's a like a non-horizontal or vertical line here. So let's see. Here's the last case then. If n is equal to exactly m plus 1, right? This is a very specific case, but these are actually just done the same way. These are both done by usually synthetic division for our cases here, all right? So if the degree of the numerator equals the degree of the denominator plus 1, then you know that all you have to do is go ahead and go ahead and go through this process here, all right? Now, it says the slant asymptote is an over bm plus x plus b, where the value of b can be determined by long division. So in other words, you should just use long division on this regardless to figure this out. So if I do that for this particular function here, x squared minus 1 over x minus 2, I have the 2, and then the coefficients of x squared minus 1, so 1x squared plus 0x minus 1. I'll bring down the 1 times 2 is 2, 0 plus 2 is 2, 2 times 2 is 4, and negative 1 plus 4 is 3. So then I get what I have here, x plus 2 plus 3 over x minus 2. And as I said before, the quotient is the slant or the oblique asymptote. All right, so this is a slant or the oblique asymptote. So here you can see it here. Here is the slant asymptote, and it with y equals x plus 2. And then there also was a vertical asymptote at x equals 2 because x could not equal 2. So x equals 2 is the vertical asymptote. All right, so hopefully you enjoyed that. But as I said, this number 3 and 4 are just really the same thing. You just have to be careful here of making sure that you get everything correct here of which case you have. Because if you have just a function with a horizontal asymptote of y equals 0, then that's the case. Otherwise, you can find the ratio of the first two terms if the degrees of the numerators and denominators are the same, or otherwise you're going to need to use long division. So even if I look back at the one that we were doing for the first example, if I look at f of x is 1 over x to the fourth, the degree of the numerator was 0, the degree of the denominator was 4, and then I knew that the 0 was less than 4, so because the 0 is less than 4, that meant that I automatically should have a horizontal asymptote of y equals 0, which I did. All right, so you can see that that's what I'm talking about here, is that I could have saved myself all of this work by just knowing that I could look at the degrees like this and see that since the 0 was less than the 4, there was a horizontal asymptote of y equals 0. So I think that was a lot easier and a lot quicker and definitely a time saver. So keep that in mind as well. So again, if you have any questions, let me know in the chat or by saying something. But the next page actually is just another couple of examples of showing functions that could have a parabolic asymptote. But I showed you one already, but there's another example of one, and here is an example of one as well. All right, so there we go on those types of examples and how, again, you would find those asymptotes. So now let's go to finding the graphs of these rational functions by transformations. So use transformations of the graph of either y equals 1 over x or 1 over x squared to graph each function, and then state the domain and range and identify the asymptote. So if we have, again, we have y equals 1 over x, that will look like this. And y equals 1 over x squared will look like this, all right? So I know that the r of x in part A is 1 over x minus 2 squared plus 1. So I see the squared. So I know I'm going to start with y is 1 over x squared. And I see here that this is what I have. And I have a point at negative 1, 1, and at 1, 1. And then I'll shift the 2 units to the right. So 1 over x minus 2 squared, 2 units to the right. So if I shift 2 units to the right, what I need you to notice is that the asymptote also shifts 2 units to the right. All right. So the vertical asymptote shifts 2 units to the right also. So then I see that there's a point at, let's see, yep. There's a point at, where is it? It's at 1, 1, and at 3, 1. All right, so now I have to shift 1 unit up. So y is equal to 1 over x minus 2 squared plus 1. So that means that the horizontal asymptote gets shifted up 1. So here's 1, and then we had the vertical asymptote at 2. So now the points are at, well, 1 and, where is it? 1 and 2. So 1, 2, and at 3, 2, and there's my graph. All right, so hopefully that makes sense that my main goal here was to get you to think about the shifting of the asymptotes as well. All right, so then the vertical asymptotes, then you can see here, they're at x equals 2. The horizontal asymptote was at y equals 1. The domain, we see that x could not equal 2, so that would be in interval notation, negative infinity to 2 and 2 to infinity. And then I see that the range y had to be greater than 1. So y greater than 1, so 1 to infinity. All right, so now let's look at another one and just keep this in mind that, again, my main goal here is to get you to think about also shifting the asymptotes, because we haven't talked about specifically shifting the asymptotes before. So if I start with y is 1 over x, so y is 1 over x, and I have a graph that looks like this with a point at -1, -1, and a point at 1, 1. All right, we know that this one has a horizontal asymptote at y equals 0, a vertical asymptote at x equals 0. So if I need to shift this, this will be shifted down 2, so -2 down 2. So, all right, so y is equal to 1 over x minus 2. So if I shift up or down, that means to move the asymptote, the horizontal asymptote down 2. So we're shifting the whole graph down 2. So 1, 2, and then the vertical asymptote stays the same. So x equals 0, y equals -2, and so that means that this point, -1, -1, gets shifted to be -1, -3. And this point here, 1, 1, gets shifted down to be at 1, -1, -1. So now I can write down my vertical asymptote, x equals 0. Horizontal asymptote is y equals -2. Domain, x cannot be 0, so negative infinity to 0 and 0 to infinity. And range, y cannot equal, what is it, -2. So negative infinity to -2 and -2 to infinity. So just remember that my range here was like a little bit different than up here, because here, like, this was an even power graph. So essentially the absolute value here, this was like applying absolute value to it. So all of the values of y started out is positive, and here that was not the case. All right, so hopefully you enjoyed that example, and now it is time for another example here. So where, oh boy, page 250, I think. So now t of x is equal to 3x minus 3 over x plus 2. Now, this is, in all honesty, a little bit of a more difficult one to do, because it's not obvious that it's a transformation of 1 over x. All right, so keep that in mind. It's not obvious that t of x is a transformation of 1 over x. All right, so now I do want to tell you a couple of things that would be important here, that the degree of the numerator is equal to 1, and the degree of the denominator is equal to 1. All right, now I want to go back to something that I did say earlier that may have seemed a little bit strange, that I'm going to go back to this page for a moment because I didn't say at the time, but in all honesty, this part right here, just so that you're also aware of this, these are actually shortcuts for the using synthetic division also. So let me explain for a moment so that you know what I'm about to do. So like, let's say that I had x minus 2 over x squared plus 2x minus 3, right? And then I tried to do this by the long division here. I know that if I do long division, then that the actually, wait a second. This is yeah. So this is where is it? Yeah, okay. So if I do the long division, then I have x and I have x squared, but I know that this x squared plus 2x minus 3 goes into x minus 2 0 times. So that's why the horizontal asymptote was y equals 0. All right, but if I look at the 3x plus 1 over x minus 2, then I know that I have, let's see, I have x minus 2 goes into 3x plus 1, and I have 3x divided by x, that's 3 times. So that is why the horizontal asymptote is just the ratio of these two terms. All right, so as I come back to this, I want to remind you that even though in practice we would only use the synthetic division or the long division if the degree of the numerator was greater than the degree of the denominator, it doesn't mean that you couldn't use it all the time, right? Because you could use this all the time. It's just that in certain cases it's a shortcut. All right. So now, so the reason why I'm pointing this out is that if the degree of the numerator is actually greater than or equal to the degree of the denominator, then a good strategy is to use long division or synthetic. Oh, I spelled it wrong. Unbelievable. All right, or synthetic division. All right, so now if I do that, in this case, I can use synthetic division. So I have, again, 3x plus 3, or is it minus 3 over x plus 2. So I have the c value, which is negative 2, so negative 2. Then the coefficients, 3, negative 3. I bring down the 3. Negative 2 times 3 is negative 6. Negative 3 plus negative 6 is negative 9. So then this can be written as a quotient of 3, then minus 9 over the x plus 2. So 3x minus 3 over x plus 2 is 3 minus 9 over x plus 2, which is negative 9 over x plus 2 plus 3. So now I see that it really is a transformation of 1 over x. So I can see that there is a reflection. There is a stretch by 9. There is a shift 2 units to the right, and there's a shift 3 units upward. All right, so then I can just graph this by using transformation. So please keep that in mind also. So now if I go ahead and I do this, then what would I get? I have, well, if I start at a y equals 1 over x, I have points at 1, 1. So 1, 1, at negative 1, 1, and at 1, 1. So like this. Then let's start by, let's see, yeah, so let's start by shifting this 2 to the right. So y is 1 over x plus 2. So 2 units to the right. So try to remember, did I say, I said right, but it's really, I have no idea why I said right, because I was about to shift it to the left anyway, and I'll tell you one thing, just so that all of you are completely aware of this, like, even if I shift to the left and I wrote right, I'll tell you my story about this, and this is why I think that the education system is really, in my opinion, really confusing to children. Is that they never taught me like left and right in school. The teacher assumed it's something that you had to learn, and so I remember the first time I figured out left and right on my own was reading it in a textbook in third grade English. So just so that you know, they don't actually teach that necessarily in schools. They sort of assume people know. So sometimes I even will move to the left and say right regardless. So um, anyway, now if I shift this 2 units to the left, that means that this is now negative 3, 1, and so the graph looks like this, and then we have negative 1, 1, so the graph looks like this. All right, and now we'll do the reflection by a negative 9. All right, so what will this end up looking like when we do the reflection by negative 9? And actually, I was going to do this step by step in the calculator too, so that you don't think I'm scamming you. But at the same time, I don't think that the calculator really will. I don't actually really think that yeah. So actually, I don't even think that this is right, because I see, this is what I'm telling you. Something didn't seem right to me from the very beginning, because I think that the real problem is that I was looking at the page on the floor, and that's why I got the left and the right mixed up actually, because this is actually, I knew something didn't look right to me. All right, so negative 1, negative 1. All right. So now I wrote the 1 over x squared because I'm looking at the page on the floor, because I don't even see the top of this page anymore. Bah humbug. All right. So now here we go. So this should be 2 to the left. So negative 3, negative 1. Sorry about that. No one said a thing, and that's okay. All right. So now I knew that this graph, I had it, the right graph in my mind, and then the worst part is that it was because I drew that graph wrong. So, all right, there we go. So now we need to reflect this, just so that you know. So y is negative 9 over x plus 2. So if I reflect this, that means that the negative 3, negative 1 becomes negative 3 and where is it? Negative 3 and yes, negative 3 and where is this? I want to make sure that I don't do the arithmetic wrong. All right, so negative 3, 9. So negative 3, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So negative 3, 9. And that means that the graph, by the way, you have to be somewhat careful about this in what you do with the asymptotes. All right, but just so that you're aware, the asymptote is going to be at where is it? Where is it? Because here okay, here. So here's the asymptote. All right. So there's the asymptote. Here's the asymptote. All right. So just so you're aware, the asymptote got shifted up like in a similar manner because of the reflection. All right. So remember that we're doing the reflection here. So the asymptote is still here, and the asymptote is still at 2. So on this graph, I'll write them out here. X equals 0, y equals 0, x equals negative 2, y equals 0. This is still y equals 0. This is still x equals negative 2. All right, so I don't want anyone to really be, how do I put this? I don't want you to be upset by this. All right, so please just don't be upset by this because I don't want you to think that this is a scam. If you want a scam, I can show you a scam later on. I really think that I can show you a scam later on. All right, I'd be more than happy to show you a scam, but this is not a scam. All right, so now this is what the graph looks like. Yes, okay, so the graph looks like this. And then this point becomes negative 1, 9. So negative 1, 9 is right here. So negative 1, 9. All right, so hopefully you don't have any questions about that, but now I have to shift 3 units up. All right, so now if I shift this 3 units up, I actually don't even know where this is why I said I think that the paper fell on the floor. I can't see the top of this paper anymore. So regardless, we have y is negative 9 over x plus 2 plus 3. So now I need to shift this graph here up 3 units. So that means including shifting the asymptote up to be the, wait a second. This is what I was talking about. This is what I'm talking about because this is not right either because you see, this is what happened to me because I only multiplied by 9 and not by negative 9. So that means that this one actually needs to be negative 1, negative 9. So negative 1, negative 9. This is why I really, in my opinion, this is why I wasn't actually, I should have just pointed my camera at the whiteboard so that this wouldn't happen and I wouldn't drop the page on the floor and forget what the function was. But in all honesty, that's what the problem is. So that's why I double checked it before I went to the next step because I only multiplied the 1 times 9 is 9, but 1 times negative 9 should be negative 9. So that's what the issue is. So hopefully it all is cleared up for you that I only multiplied by 9, not by negative 9. But in either case, if I I shift this up 3 units, that means that I have to move the asymptote up to y equals 3. The vertical asymptote is still at x equals -2. And then I need to add 3 to the y value. So this is why I said before the last one, I wanted to make sure my arithmetic was right. So let's me make sure that I get 9 plus 3 is 12. All right. So now, 9 plus 3 is 12. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 9 plus 3, 12. So I have -3, 12 here. And here's what the graph looks like. And here I have -1, -9. -9 plus 3 is -6. So 1, 2, 3, 4, 5, 6. So I have -1, -6. And then you can go ahead and be as accurate as you would like with these, but I really don't think that it matters, in my opinion, too much, because at this point it just looks something like this. All right, so so it was -1, -6, and that is the final graph here with the arithmetic correct. Like not 1 times -9 is 9 or something weird like I did that other time. All right, what a time to be alive. At least hopefully you have that arithmetic right now. But in either case, that means that the vertical asymptotes are... Oof. This is why, by the way, I'm going to point something out to you in a minute, but the vertical asymptotes are x equals -2. The horizontal asymptotes are going to be y is equal to 3. The domain is going to be -infinity to -2 and -2 to infinity. So x cannot equal -2. And the range is going to be -infinity to 3 and 3 to infinity. So I'm going to point one thing out to you to be absolutely clear on this, that graphing these types of functions using transformations is going to lead to like issues like I had with drawing the wrong graph by accident, even if it's an accident. Like like I said, I thought I was graphing 1 over x squared when I graphed this, but even if it's an accident, like multiplying by the wrong number, by 9 or -9, like all of these little transformations can add up to a lot of errors. But if I look at t of x is equal to 3x minus 3 over x plus 2, and then I know that the vertical asymptote is when the x plus 2 cannot equal 0, so x cannot equal -2, so it's x equals -2. The horizontal asymptote is going to be the ratio of the leading terms here, because the degrees were degree of the numerator equal the degree of the denominator, right? So I know that it's y is 3, x over x is 3. Then I can already tell you that I know what the graph looks like. It's 2, and then it's 1, 2, 3, and then I know that all I really need to do is substitute some, maybe a number here to figure out where the graph is located. So x and 3x minus 3 over x plus 2. So if x were, say, -3, 3 times -3 minus 3 over -3 plus 1, that is, well, -12 over -1, that's 12. Well, look, I just got -312, which is the same point that I got up here. All right, so then I have -312, so 4, 5, 6, 7, 8, 9, 10, 11, 12. So -312, And then because I know that it has to approach the asymptotes, I know that the graph has to look like this. And then if I pick a number sort of like if I pick 0, I get 3 times 0 minus 3 over 0 plus 2. That's negative 3 over 2. So negative 3 over 2 is right here. So then I can just graph this so it looks like this. All right, and if I wanted to pick negative 1, I could. 3 times negative 1 minus 3 over negative 1 plus 2. That would be negative 6 over 1, which is negative 6. So I still get the same points as if I would have graphed using transformation. So hopefully you can see that my strategy would be never to use transformations because of the issue that you have 4 graphs to draw, and the likelihood of you making a mistake when you're drawing one of the graphs, like I did, like I wrote down the wrong graph to begin with, and then I multiplied wrong and got 1 times negative 9 is positive 9 when it wasn't supposed to be, then you're at a higher risk for making a mistake. So just try not to use transformations. I know that like some people like to use transformations, and that's why it's still really a thing, but it's really just it's one of the options you have to graph these. But yeah, so hopefully that all makes sense right now. So now it is time for another example here. So the last couple of examples are just like putting this all together, sort of what I was just doing, but without using the transformation. So we're going to go through all these steps and sketch the graph. So factor, find the intercepts, the vertical asymptotes, the horizontal asymptotes, and then sketch the graph. So locate any asymptotes and display the asymptotic behavior graphically. Okay, so here we go. So the numerator and the denominator are factored already, but what I'm actually going to do is I'm going to rewrite f of x so it's 4x plus 1 over negative x plus 3. And I know that if I want the x-intercepts, then I let the y will be equal to 0. So 4x plus 1, the numerator will be 0. So 4x will be negative 1. And if I divide by 4, x is negative 1/4. So one of the points on the graph is negative 1/4, 0. Then if I want the y-intercept, I can let the x equal 0. So then f of 0 is 4 times 0 plus 1 over negative 0 plus 3. So that's 1 over 3. So this is 0, 1 over 3. All right, so that's it. Now I find the vertical asymptotes. So then the vertical asymptotes, I know that the denominator cannot equal 0, so negative x plus 3 cannot equal 0, negative x cannot equal negative 3, and x cannot equal 3. So x equals 3 is the vertical asymptote. And then I find the horizontal asymptote. So horizontal asymptote, and then if I do that, then I have that if I look here, 4x plus 1 over negative x plus 3, the degrees are equal, so the degree of the numerator equals the degree of the denominator. So it's the asymptote is the ratio of the leading terms. So 4x over negative 1 is negative 4, so y is negative 4. And now all I need to do is sketch the graph. So if I sketch the graph, I have x is equal to 3 is one of the asymptotes, the vertical asymptote. I know the horizontal asymptote is at y equals -4. And then I know that there's a point at -1/4, 0. So -1/4, 0. And a point at 0 and 1/3. So 0 and 1/3 is right here. So all I really know right now is that this part of the graph looks like this because it goes through those 2 points, right? So that means that I need to find out what happens over here, and I could just pick f of 4 and figure it out. So if I pick f of 4, that will be 4 times 4 plus 1 over -4 plus 3. That will be, is 17 over -1, so -17. So 4, -17 is another point on the graph. So that 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we have 4, -17, and then I think that hopefully you can get an idea, a picture in your head of what this graph looks like, and it looks like this going toward the asymptotes, all right? So now it did ask for the asymptotic behavior, but all that means is what is happening as x goes to -infinity, then that means y is actually going toward, what is it, -4, as, okay, so what are the other ones that we have here? I just want to make sure that we say all of them, all right? So, that's okay, we don't really need to say anymore. Okay, as x goes to infinity, remember that y was still going to -4, and then as y goes to infinity, x was going to be close to 3, and as y goes to -infinity, x is going to 3 also, all right? So now that, so this is actually 3 from the left, all right, and this is 3 from the right. So if you want to make sure that you're clear, 3 from the left and 3 from the right. All right, so keep that in mind, that this is what they mean by the asymptotic behavior. Now, the other thing is, don't forget to solve the problem that they asked us for, and that is to find where f of x is less than 0. So f of x is less than 0 over here and over here. All right, over in this portion of the graph, the f of x is actually positive. All right, so that means to solve this inequality, I'm just going to look at the graph, and f of x is less than 0 from -infinity over to -1/4. All right, so -infinity to -1/4, and from 4 all the way to infinity. So in 4 to infinity. All right, so I hope that you enjoyed that. All right, that one, oh no, the highlighter, it went on the floor somewhere, so if the blue highlighter doesn't come back, that's why. Actually, I think it may have been the orange one. I'm just glad I don't have any cats, because the cats would have knocked all the highlighters under the couch by now. That's why I don't like my mom's cat. She always puts things all over the place in the house, and I never know where they're at whenever I go to help my mom. My mom says something's missing, and then it ends up being under the couch for 20 years. All right, so, like, it just, you never know. All right, so now, hopefully, again, if you have any questions, feel free to ask in the chat. But let's do one more here. So f of x is equal to 2x to the third plus 3x over x squared minus 1. So let's start here, and remember that the step 1 said to factor the numerator and denominator. So if I factor this, I have x times 2x squared plus 3 over x plus 1, x minus 1. All right, so now the next step was to find the x and the y-intercepts. So let's find the x-intercepts. So we're going to set the y equal to 0. So the numerator equal to 0. So x times 2x squared plus 3, set that equal to 0. So x is 0, or 2x squared plus 3 is 0. But we know that this one will be imaginary, so this one is not going to be a real 0, so not a real 0. So we're not going to worry about graphing that 0. So there is an intercept at 0, 0. All right, now the other thing is that we need to look at the other intercepts, the y-intercepts. So let's look at the y-intercepts now. So set x equals 0. So f of 0 is 2 times 0 to the third plus 3 times 0 over 0 squared minus 1. Well, that's 0 over negative 1, which is 0. So we get 0, 0 is also the only y-intercept. All right, so now we need to find the vertical asymptotes. So this is just where the denominator is equal to 0. So the vertical asymptotes. So we know that here we have x plus 1 cannot equal to 0. X minus 1 cannot equal to 0. So x equals negative 1 is an asymptote, and x equals 1 is an asymptote. So these are the vertical asymptotes. And now I want the horizontal asymptotes. So we have any horizontal asymptote. So f of x is 2x to the third plus 3x over x squared minus 1. The degree of the numerator was 3. The degree of the denominator was 2. 3 is greater than 2. So that means that if the degree of the numerator is greater than the degree of the denominator, that means that there is no horizontal asymptote. All right, so that means no horizontal asymptote. But I can use long division to find a slant asymptote. So I'm going to use long division to find the slant asymptote. So if I do that, I have x squared minus 1 goes into 2x to the third plus 0x squared plus 3x plus 0. So, 2x to the third divided by x squared is 2x. So 2x times the x squared minus 1 is 2x to the third, and then that will be minus 2x. So if I subtract, I get 5x. But remember, this is the quotient, and this is the remainder, but the slant asymptote is just equal to the quotient. So the slant asymptote is y equals 2x. So now, let's see. Now, we have the asymptotes. We have the intercepts. Now we can sketch the graph. So let's do a sketch of the graph. So here is a sketch of the graph here. So sketch. All right, so we have vertical asymptotes at x equals -1 and at x equals 1. And then we have a slant asymptote of y equals 2x. So there's an intercept at 0, 0, but a slant asymptote of y equals 2x. So at 1, I actually have a 2, and at -1, I actually have a -2. So I know that the asymptote actually looks like this. All right, so now I need to know sort of what is going on in between these asymptotes. So all I really need to do is remember the function was f of x was 2x to the third plus 3x over x squared minus 1. I just need to graph the viewpoints just to see, all right? So, and by the way, I I really am not going to be that particular because I said it's a sketch. I mean, I already can tell you that without even knowing much about this, that this graph is going to go like this in here, and this in here, and go close to its asymptotes. All right, but if you want to know what this exact point is, then that will take a little bit more work, and that's what requires the calculus to find that exact point. That's why we're just sketching it. So I really just need to know mainly what's going on in the middle part, and I could do that by substituting a point. So if I had, let's say, I'll show you here. Let's see. Here it is. Uh-oh. All right, here it is. So if we had 2x to the third plus 3x divided by, let's see, x squared minus 1. Again, this is what the graph would look like. And you can see that it did get really close to the y equals 2x. But if I want to pick specific values, I could substitute in, say, a -2, and I get -2, -7.33. So -2 and 2, 3, 4, 5, 6, 7, so 0.3. So this is like, there's a point at -2, -7.33. All right, so don't get too upset about this, but again, I want to show you maybe something in between -1 and 1. So let's try a -0.5, -0.5, 2.33, and then if I have 0.5, I have -2.33, so 0.5, -2.33. So the graph looks something like this. All right. So, by the way, as I said, if I go back to zoom standard here, I could actually figure out what that point is. So if I want to calculate the maximum value over here, let me just well, okay, there, and it's at -1 point. It's -1.17, negative. Oh well. Anyway, that doesn't make any sense. This calculator is not the best. I'll tell you that. But I think that the calculator is doing something very strange. But anyway, I think you get the idea. I did want you to see that though, like just so that you know that I'm not trying to scam you. All right. So, oh no, you see that? Like this calculator is a scam here. So just be aware that yeah. Yeah, that you're getting scammed whenever you buy a calculator these days. All right, so now let's go ahead and graph another one here. So where is it? The last one here. Oh, by the way, you could list the asymptotic behavior for this one. So asymptotic behavior would be x approaches negative infinity. Well, this one, if you see what's going on, though, remember that the y was actually just not approaching a number, so that one would not be really anything except y approaches like 2x, all right? And is x approaches infinity, y was also approaching 2x, and then y approaches negative infinity, and as x approaches, what was that? That was negative, was that negative, where negative 1, all right, negative 1 from the, oh, from the left, all right, that would be this one right here, and then y approaches infinity as x approaches negative 1 from the right. That would be that one right here, and then this one would be as y approaches infinity. That would be as x approaches 1 from the right, and y approaches negative infinity. That would be as x approaches 1 from the from the left. All right, so there's a lot going on here, but I think that, in all honesty, it's not very important necessarily to write this out because all of it can be described by the graph as well. So there's one more example. This one should be quick, and then that will be it for today. So this one, all right, let's go through this one, just the basics here. So the numerator and denominator are already factored, so now I need the x-intercept. So I let the y be 0, so that would be 2x equals 0, the numerator equals 0, so x is 0, so 0, 0 is an intercept. Then for the y-intercept, I let x be 0, so f of 0 is 2 times 0 over 0 squared plus 1, that's 0 over 1, 0. So it's also 0 over 1 is 0, so it's also 0, 0 for the y-intercept. And then I need the vertical asymptote. But if I look at this, I know that x squared plus 1, the denominator, if I set that equal to 0, I get x squared is equal to negative 1, but that is imaginary solution here. So that means that there is no vertical asymptote, no vertical asymptote at all for this function here. And then I can find the horizontal asymptote, there we go. So if I find the horizontal asymptote, then I just look at the degree of the numerator and the denominator. So f of x was 2x over x squared plus 1. Degree of the numerator was 1. Degree of the denominator was 2. So 1 is less than 2. So that means that the horizontal asymptote is just y equals 0. So, well, now I just need to go ahead and graph this. So I know that there is a point at 0, 0, and that the horizontal asymptote is y equals 0. And then I also know that there were no numbers that would make the denominator equal to 0. So that means that the domain is all real numbers, negative infinity to infinity. All right, so now I can just substitute a few numbers here just to get a sense of what this would look like. So x and f of x is 2x over x squared plus 1. So if I substitute a negative 2, I get negative 0.8, negative 1, negative 1, 0. I already knew I get 0, 1, 1, and 2, 0.8. So if I have 2, negative 0.8, it's about here, negative 1, negative 1, 0, 0, then I have 1, 1, and 2.8. So this one seems to go and have a little dip, and then come up, and then have a dip back down to the asymptote. So this is a strange one to graph here as well, but again, to figure out these points right here and here, these peaks, these relative minimum and maximums, that's where we would bring in the calculus to get more exact on that easily without using a calculator. So that's it for this section on rational functions and graphing rational functions.